Welcome back. Here we are again, looking at the Foscam R2C camera, and we're going to continue our hacking process, hopefully to achieve remote code execution. So if you haven't seen the first two episodes, definitely go back and check those out. We have shown how we identified some of the hardware components, and we're able to get console access to the device, as well as dump the flash in the last episode. So now that the flash is dumped, in this episode, we'll start diving into some of the ways to extract files from the flash dump, as well as start reverse engineering some of the interesting binaries that we've found in that flash dump. And then we will also continue to try to de-obfuscate the encryption password for the firmware updates. So hopefully that sounds fun, and we'll catch you at the end. All right, and we're back. It's a new day, got some coffee, so let's dive into that firmware that we just dumped. We definitely took a look at the binwalk output yesterday and saw that there's a bunch of compressed data. Like there's probably the U-boot image right there. You can see the U image header. There's a squash FS file system, which is usually good. Most of the times that's kind of where the read-write Linux operating system is stored at. So let's try to extract some of this stuff. Binwalk actually allows you to just run this -E for extract. Let's give that a go. We'll try to pull all this stuff out. So I can go into this dump, extract in. Holy cow. So we see some good stuff. Let's dive into that Squash FS folder here. So cd Squash FS TV. Okay, so there's like an app. So what I'm trying to think of is we're trying to find something that we could potentially, attack or figure out the password for that firmware update that we got. So that's kind of where I started down this project, is I just wanted to get to that password. So thinking of that, change password text. Sounds kind of interesting. Let's view that. Okay. Pure password. What's that? Maybe that's for since it's database maybe related. Maybe that's for the users on the web interface or whatever that you make. I don't know. This doesn't look too familiar for anything like Linuxy. So it is a binary, pure PD. Well, that's cool. Let's keep trying to find something that's maybe firmware related. Yeah. Oh, there we go. I bet this has the password in it. So let's just go there. Since if you think about the process where you upload this encrypted blob bin file, it has to decrypt it through some sort of process, and that is, I don't know, in my eyes, a firmware update. So this seems like a good bet for which binary is actually doing that. So let's just see what it is. So it's an executable ARM. All right. So maybe let's load it up in IDA and take a look at it. Actually, let's do it in Cutter because it's free, and if anyone's following along, maybe they can, because it has free decompilers from Ghidra. So let's do that and just try to see what we can do from there. All right, so I loaded the firmware update binary into Cutter. So let's try to take a look at what we can see in here. What I like to do is just go to strings right off the bat. Let's try to find, I don't know, decrypt. Decryption failed. So this is kind of a good way to actually start finding things that you're interested in, is look for words. And a lot of times they add debug statements, so it prints to the log, like in this instance, decryption failed. That can help you when you get to where you can help find the code where it's actually being referenced at. So decryption failed. So that's getting loaded here. So if we open this up in the graph, so log write, firmware open, decryption failed. So it's printing that here. So this path must have failed at some point. So let's try to open this in the decompiler, see if we can read it a little bit better. This to me looks like could be the passwords or something. Reform string. What does a reform string do? This might be imported. Let's check in the imports. Reform strings. Yeah, it's getting imported. So we probably won't be able to see that unless we find which library has that reform string. And let's try to figure that out. So let's head back over to the terminal. So we're trying to find a thing called reform string. So that usually on Linux, all like shared objects or shared libraries usually have the .so. extension. So let's try to find something with that. So dot name star.so. And sometimes they add version numbers afterwards. So I'm going to give another star. So here is all the SOs on this device. And so as you can see that there's like a crypto ones that could have it possibly, but one of the things we can do is actually run like objdump on this. I think I have to have arm objdump. Let's just try this crypto one. Let's pass it -d. Yeah. I think I need arm objdump. Oh, I do have one. Cool. -d. Okay. So that is doing that. So it's actually pretty much doing what the cutter was doing, but just using a Linux command. But you can see that it actually will print out some of the stuff that it has. And if we can maybe make a little script to automate through all of those to try to find the one that has the reform string, I think that could help us try to narrow down what we're trying to do here. So actually thinking about this a little bit more, I think actually objdump it would probably work, but nm might be actually a better thing. I do have that installed too, so let's just try nm. Passing the -d again and giving it the command or the SO. Yeah, okay, so this looks much cleaner, easy to identify what things are getting exported. So let's script this up. So we want for I in I've kind of done something similar before. And instead of check sec, let's do arm none ebnm -d. So this is going to go find all .sos like we just did, save them each one by one, save them to F, just print off F, which so we know what it's doing, and then pass this into this function, and then we can go like this and go grep for what was it called? Reform string. And then enter. Let's see if this works. No. Okay, so it looks like common lib has a reform string, and so does lib encrypt. Which one should we look at? Kind of lean towards lib encrypt. Let's do lib encrypt. So I'm going to open that up in Cutter. So this is the lib cutter. Lib encrypt, not lib cutter. And we're going to try to find where this is calling reform string. So reform, yeah, that was it. Wait, is it importing it too? Oh, it has a, so see how it's I don't know, underscore Z12. I think we need to actually type that in. So back over here, underscore Z1, nope, capital Z. Let me just copy it from the terminal. So this is what we're actually looking for. And this one doesn't actually have it. So maybe we should check out the libcommon one. Okay, so now we have libcommon open. Let's try to find, what the heck? Oh, here it is. Okay, so it's in libcommon. Great. Let's open that in the decompiler. Oh, weird. So it has a has like a readable name over here, and then it has underscore Z12 over here. Nice. Okay. What is this doing? So these are both ints, arg1 and arg2. They could be pointers. Might possibly be pointers. So what I think it's doing is I think these are pointers, arg1 and 2, and I think it's showing that it's not null. It shouldn't be. Why is 4 equal? Okay, yeah, 4 equals 4, 2. Oh, wait. And all right, this isn't very helpful. Okay, actually, let's just take a look at this in IDA. I feel like the Cutter Ghidra decompiler isn't working as well as I hoped. So let's just hop on over to IDA now. So this is the firmware upgrade. So let's just do the steps that we've already done. So let's search for, actually open up strings, search for decrypt, decryption failed, go here by xrefing. Alright, decryption failed. And now if we open this in the decompiler, we can see, oh, much easier to read. So it's accessing a file. Oops. Trying to get this window a little bit closer so I can see it. Of course, it's changing.
Okay. Oops. Which 7? Okay. So where was that reform string? Reform string, okay. So, oh, this makes way more sense. So it's passing in a char star of a pointer that v28 is just an int. So int's gonna be a pointer. And the mem setting v29. Okay. And they're making a directory temp firmware upgrade. Cool. So now let's just take a look at what that reform string looks like too. So I have that pulled up in this window. Let's search for reform string. Okay. Decompile it. VA copy. I wonder what VA copy is. Oh, variable arguments. That's it. Okay. So A3 might actually be the size. I think it is. So let's just name it size. And we could see from when we called it in the previous window, it looks like they passed just all characters as the second argument. And that one is definitely different, so that's probably the size, yep. So the second one is going to be a constant character list. And then the result. Okay. So it doesn't save it anywhere, does it? If result. I still think that's a pointer to the char star. Yeah, okay. Yeah. So it's the address of the result. And if it fails, they put a 0 into that address. Okay. V4 is what? 0. Well, V4 does not equal size. Loop through. Okay, so that's just incrementing. V6 equals V5. So we can name this dest index. And then V6 is the index in the chart character list. Wait, is all it doing is just taking byte equals result plus index equals index of the character list? Is that all it's doing? Is let's just try doing that by hand. So I'm wondering if all it's doing is just 14 means the 14th character in this row. And this is, I'm guessing, 30 hex, which is in decimal 48. So let's check the size. So 73 to 220. 173 220 minus 247. Oh wait, why is this? That's not what I was looking for. Can I get it? 220 minus 47. Okay, that was right. I'm used to it being Python, not IDC. So 40. Oh wait. 48. Yeah, so that makes sense. Because it's including itself. Okay. Alright, so now that we know the size of, so that's is definitely the size. Let's just try to go 14. What's the 14th character in here? 1, 2, 3, 4, 5, 6, 7, 8, 12, 13, 14. N or O? Oh wait, it's 0 index, so it would definitely be O. O. P. E. It just seems like that's exactly what this is doing. It's just the offset. So 13 is 1 before O. N. Okay. Well, that's easy enough. Forget compiling code or trying to load this into a load this shared object. Let's just copy this and yeah, and let's just do it into the terminal. So yeah, this is, let's change this to Python. So let's not even save this. Python, because I know how to do Python much easier. And then paste char list equals, that didn't copy. There we go. And all of these. So there's actually a 0. Oh, it would be A. Okay, yeah, that makes sense. Okay. Oh, actually, no, this would just be charlist. Let's give it a go. Hey, look at that. So it gave it actually the whole command. So open SSL, encrypt, decrypt, AES 128, MD5 with the key. That's the password. Heck yeah. Nice. Let's give it a go. So now that we grabbed this key, we can go back to the original upgrade, this original bin, which we know is encrypted. So file Foscam, so it's a encrypted data with salted passwords. So now if we give it this and then dash I66, then pipe this out to Foscam.decrypted. So that's just a warning. I think that's fine. So now let's do file gzipped compressed data. Okay, so let's just do bin walk on it too. Oops. Okay, XZ data. That thing, this looks like it's just a compressed file, so let's extract it. All right. So we got some files out. There we go. So that is how we would encrypt a blob and decrypt it. So at this point in this real world CTF challenge, we can potentially try to exploit a malicious firmware update. For one, granted that we have the password is going over plain text because SSL doesn't work anymore. So we can always just log into that system that we showed on the VM. Instead of downloading the correct firmware, we can actually supply it with a malicious one and potentially get code execution. So let's try to figure out if we can do that by trying to exploit this firmware upgrade process a little bit more. So one of the things is we still don't exactly know how it is actually like extracting all this and whatnot, because if we go back to our dump of the flash, Where was that? That was in here. Dump. Okay. Find name. We still don't actually have the Linux operating system, if that makes sense, extracted. So like tar, for instance, isn't still found in our firmware dump. So that leads me to believe that we actually haven't extracted that RAM disk that we have access to from the U-boot menu that we've done. So if we go back to I'm going to plug in the device again. I'm not actually going to do that because I'm worried that I still have the Raspberry Pi hooked up. I've moved it a bit out of the way because it was definitely in my keyboard zone, but I still have the Raspberry Pi hooked up, and I don't really want to mess with those pins because it seemed to work last time we used it. And I'm worried if I unplug it, then it's not going to work again if we want to actually flash anything back. So let's just keep diving into maybe the extracted dump and see if we can find any other potential file system. So JFFS2 is another kind of similar to Squash FS, like a file system format. Except for it's weird that there's so many of them. And if we go back to just bin walking, dump bin, why is there so much stuff? I'm trying to think of what to do. I don't really want to slug through all this and try to find which one of these is the actual file system. We could try doing, let's try running it with recursion on. So if we move the extracted dump to the first one, and now if we bin walk -E, I think it's Matroshka. So capital M, recursively scan extracted files. So let's do EM. So this will recursively extract hopefully all the stuff inside of it, which could be just a complete pain because it's extracting a lot of stuff, or it could be really cool. Things are really cooking. Wow. This is, okay, I was going to say taking a long time. So now, we go to the extracted, extracted everything. You extracted the PNG file. Okay. hopefully now if we search for instance, tar. Okay, we found it. So now CPIO root. Okay, so that's probably how it's extracting the file at least. So let's go to that. So this is most likely the Linux operating system that probably we get dropped into. Yeah, nice busy box. This is probably what we actually are getting dropped into when we are exploiting the bootloader init command. All right, so I just want to try see what BusyBox version this is. Okay. LD path. LD Linux RMHF. I wonder why that didn't work. Cannot open. Oh, it's like trying to look at it from the root. I'm wondering if it just maybe it's because it's just trying to use a relative address. So let's just do spaces in the name. I hate that. Lib. If this doesn't work, oh well. Alright, it's not working. There's definitely a way to run things like that. By giving it the path. I thought that was it though. But maybe it's like hard coded or something. Anyway, so let's dive back into IDA and actually see maybe if we can identify what happens now after it extracts the password here. So now that we know that it extracts, let's try this one too. I wonder what this one is. Because we only did that bottom one. There's two reform strings. It looks like it starts off the same. This one is longer. Okay, so back to the terminal. Extract password and extract. So let's do P1. P2 equals. What? Oh, jeez. I know there's a smarter way for all the people that use Vim out there to do than this, but at this point I feel like it would take longer for me to Google how to do it correctly than just doing it like this. So sometimes the right way is not always the easiest way. We're done. Okay. Let's just yank these 5 lines. Paste them right down here. Change this to P2. Okay. So that's more of kind of how we extracted it. So interesting. Multiple ways. So this bottom one is actually the top one in IDA. That's not confusing enough. So this is the one, the longer one that has the dash in. God. Mowing the lawn now. So, sorry about that. So V28, which is the result, remember? Result, jeez, is getting put there. So that's actually the second one. So that's cool. It's like the black box of that. So it DD's this first one, which is A2. Where's A2? A2's passed in. So let's just see if we can find. Okay. So I'm wondering if that's actually our uploaded bin file. And maybe when we upload it to the device, it saves it at this temp online package bin, which is in A2. So this could be renamed to update bin. So it's DDing that update bin, and when you don't have an OS with DD, it just prints it to standard out. So it's getting piped into the black box OpenSSL command, and then getting tar zxf extracted from standard in, and then this -c, if I'm correct, what is tar dash capital C directory. Change to directory before performing any operations. This operation is order sensitive, i.e. it affects all operations that follow. Okay, so we're CDing at this point into this temp upgrade folder. I'm trying to pull out this patch upgrade config.xml. And if that happens successfully, so then it's gonna run that in the system. So that's this whole string, because it's sprintfing into that. So all of that gets put into this. And if that happens successfully, we get V13. And then we do a bit mask on it. And oh, okay. .127 as a return code usually means command's not found. So maybe it's just bit masking that. Okay, let's try running this actually. So if we copy all of this and fill it in on our stuff, let's just make a temp directory. So that's where we're going to CD to. So now if we run this with just this dot temp, /, this is going to be our, this command, black box extracting or decrypting, and then this is going to be our foscam.bin. So we got a return code of 2 because it looks like patch upgrade config.xml not found in archive. So if we bit mask 2 with 127, 2 and 127 equals 2. Okay. That is right? Yeah. Okay. So 2, so this just equals 2, does not equal 0. It exists abnormally. So OpenSSL exists abnormally, and then returns -1. But if it passes that, so if there is a patch upgrade config XML, then takes the high byte of it, what does tar return? So we're trying to look up, maybe it's like return value first. Return value, successful termination equals 0. one, some file, fatal error. Okay, so that's what we got earlier. So if patch upgrade does not exist, it exits. But if it does exist, it will take the high byte of that, which is 0. And if 0 here, it would fail. I mean, if it's greater than 0, it would fail. If not, it goes into here and sets this to 1, and then checks that if it's 1 or greater, it does a unsecure tar extraction. And the reason this is unsecure compared to these other ones is that it's not actually pulling out a specific file. So when you add a file like this with the X flag, it actually tries to find it inside of the tar archive and extract it. This one is just extracting the whole archive. And we could potentially use this tar extraction to exploit this a little bit further by potentially adding like a symlink or something that it can extract into, and potentially overwrite files on the system, leading to like an arbitrary code execution. So it looks like we need to actually be a patch file. If it's not a patch file,